So I'll just be reviewing some of the things for the midterm, especially from systems point of view. So whenever you're told that you have a system, think of it as a black box. You don't know what the system is doing, you just know what the input and what the output is. Okay, so your input is x of t, your output is y of t, and let your system have an impulse response of h of t. So just to clarify all the terms, h of t is the impulse response, that is the output y of t when x of t is an impulse. Alright? Okay. Now, in the exams you could also be asked for a step response. Okay, so let me write step response as h of st. So step response is analogous to the impulse response. That's when x of t is equals to u of t. Right? Okay. So when you apply x of t as equal to delta t, the output that you get is your impulse response. When you apply x of t is equals to u of t, which is the step function, the output that you get is the step response. Alright? Just be clear with these terms. Okay. H of s or h of z is your transfer function. And if this is given to you, h of s or h of z is given to you, you take the inverse Laplace and get h of t, or take the inverse z transform and get h of m. Always remember that h of s is related with continuous time signals and h of z or z transform is only for discrete time signals. Do not mix the two. Okay? Alright, so another thing that I wanted to cover was poles and zeros. Okay, so let's say that the h of s, so poles and zeros is only associated with your transfer function. H of s or h of z. Alright, so let's say that we have h of s is equals to 1 over s plus 2, s plus 3. Very simple example. So zeros are the roots of your numerator. And poles are the roots of your denominator. Oh, so. Alright. So zeros, roots of numerator, poles, roots of denominator. So you could also be asked to plot the poles and zeros. Okay. So whenever you plot your poles and zeros, they'll be in the complex plane. Alright. So if you, h of s is given to you, you'll have real of s and imaginary axis. And if h of z is given to you, this will be a z plane, but again complex, because your poles can be complex. Okay, real or complex, right? So always denote your poles with your circle and your zeros with a cross. Okay, so for the given h of s, what zeros do we have? None, right? So no zeros in our case. And poles? Correct. So poles are at -2, -3. So you'll just mark your poles. Oh wait, I mixed this up. This is zeros and this is poles. Poles are with crosses, zeros are with your dots. Okay? All clear? So remember, zeros are the roots of your numerator, poles are the roots of your denominator. And it's the poles that control your stability, right? Because it's the denominator that we're concerned with when we look for stability. Okay? All right.
But the stability of the poles, that one is only for Bible, right? Because the transfer function, we don't know.
But if the if the denominator represents your characteristic equation,
Then it weighs both.
then it handles both of them.
But if not, then it's only Bible.
Then it's only Bible.
Okay.
Right?
Is the plotting the same as in the Z transform also?
Yeah, it's the same. So let's say for Z you have some h of z equal to z minus 3 over z minus 5, z minus 6. Let's say. Oops, sorry. So you're plotting, what will be a 0? Correct. Yeah. So plus 3 and poles. So 5 and 6. Okay? Right? Yeah.
Can we get an example where something cancels?
Sure. Let me think of an example. So let's say h of z is z minus 1, z minus 2, and here you have z minus 1, z minus 3. Yeah, I think that's enough, right? So we have a 0, let's say real z, imaginary z axis, this is the origin. So we have poles at 0, 1 and 3, right? So 0, 1 and 3. And zeros are at 1 and 2. So the 0 at 1 will cancel the pole at 1. Okay? So you'll have a pole 0 here as well.
So actually you don't have anything, right? Like that transfer function, when you analyze it, if you're given it like that, you know, but you might be given it simplified, and you would never know.
Yes, you would not know if it's simplified.
So if you cancel it out and then plot it, then will it be wrong or?
No, it'll be correct.
Right.
Yeah, that'll be fine.
So the one shouldn't have anything on it, or it should have both?
So if you're writing it like this, it should have both.
Okay.
If you're cancelling it, then it will not have anything. Okay? But it's just to give an idea over here that, so basically this comes in handy when you're designing filters. So let me give you an example of a filter. All of us know what filtering does. We get a output at specific frequency. Okay? So let's say this is my frequency, some value. Okay? And I want my response to be like this. Okay? I want my filter to pass everything apart from this frequency, let's say f0. Okay? So this type of a filter is called a notch filter. Okay? And how do we design this type of a filter? For this one, we just put a pole and a 0 very close to each other. Because if you think of a realized system, you cannot actually have the same values. Okay? So the poles and the zeros are very close to each other, like here or somewhere else, wherever this frequency is. And this is Z domain. So this frequency runs from 0 to pi. Okay, radians, in terms of radians. Alright, so let's say this is pi by 2. So I'll have a pole and a 0 here. Okay?
Why is 0 on the right side?
What side?
You have 0 there and pi on the left.
Yeah, so I don't want my pole to be outside the unit circle. So the value of my pole will always be less than 1. And my 0 can be anywhere. It can be outside or inside.
Shouldn't the plus plane be negative? Or is that like a negative pi and plus?
Yeah, so negative pi and plus pi, they all correspond to the same thing. This is in terms of radians. So it starts here. Think of it as an angle. It starts at 0, goes up to pi by 2, and then pi.
So the poles are inside the unit circle?
Yeah, for stability. The poles have to be inside the unit circle in Z domain.
Okay. And the x's are?
They can be on the unit circle or outside the unit circle or inside the unit circle.
Okay.
Because zeros do not affect our stability. It's the poles that affect our stability. Alright? So this is an example of your pole 0 location where it comes into play.
When you were asked to find like stability asymptotic in Bible,
Mhm.
a question like this where it cancels,
Mhm.
what do you do then?
So you can actually say that you can assume, like you've done in the homework, that the denominator is the characteristic equation.
And this way it affects both the
Bibo and the asymptotic, yeah.
And if something cancels, do we cancel it and then do that, or do we just not cancel it?
I noticed in exams, you usually only ask about Bible. About
Yes,
that problem.
yes, because obviously there's a confusion between Bibo and asymptotic. Because for asymptotic, you have to assume that it's the characteristic equation. Because you don't know if it's already been simplified or if it has not been simplified.
So just keep it as is without simplifying and then find the stability.
Yeah, so if you're finding h of z and h of s, then that's the way to go. But if it's given to you, then assume that the denominator is the characteristic equation and then go forward. Okay? Okay, so another thing is dealing with block diagrams in the exam. So I'm just going to go over a few block diagrams that's given in the test. So this is the fall 2010 exam. So this is a very simple one. There's nothing to it. Here it's given that your system is an integrator. Right? It's given to us. And the simple question is to find the impulse response. Okay? So for impulse response, what would be my first step? And let's say this is h of t. How will I go forward to find the impulse response?
The matrix dBdt.
Correct. So my h of t will be an integration of delta t dt. Correct? And that is u of t. So this is my impulse response.
Wait,
Right?
Why is h of t equals that, not y of t?
So y of t, okay, let's do this. Y of t when x of t is equals to delta t is h of t. Okay? In general case, y of t will be the convolution of h of t and x of t. Okay? Alright? Okay. So now, how will you find the transfer function from here? Correct. Correct. So you have h of t is equals to u of t. Transfer function is h of s, right? It's not h of z in this case because it's continuous time. You won't take a z transform. So you'll have 1 over s. And real of s greater than 0. Okay? It's a good idea to include the ROC in your answers.
Do we have to?
It's a good idea.
You need to include what?
The ROC.
Oh,
Okay?
Is it not be part of the array?
I don't seriously know because that's his, but just write it.
Yeah.
It's a good idea to include it.
Solutions we always put it.
Yes. It's just being thorough with your solutions. Okay? Now, let's say again we have some other block diagram. Let me go to the next page. Okay, so let's say we're given the following block diagram. Oops, sorry. All right, and my task is to find h of s. So h of s is y of s over x of s. So I need to find a relation between y of s and x of s. Okay, it's a simple loop. Okay, just write these equations. So first I'll just write e of s. What is e of s? E of s is x of s plus k y of s, right? E of s has this thing, has x of s as an input and y of s times k as another input, and both of these are added together. Okay, that's where you get e of s equals to x of s plus k times y of s. All right, now y of s is equals to g of s times e of s, correct? E of s being fed as an input and y of s is the output. All right, next step is to just substitute what we've got. So my y of s is now x of s plus k y of s g of s. I have just substituted e of s. All right, and now just get the common terms on the same side. Okay, so I'll have y of s minus k g of s is equals, sorry, 1 x of s times g of s. So y of s over x of s, which is my h of s, is equals to g of s over 1 minus k times g of s. Okay, and in such a question g of s would be given to you. Yeah.
How do you know that E of S and G of S are being multiplied? It's because they're cascading systems.
So E of S is the input and G of S is a system. So so G of S over here is a system itself, right? So in S domain, my output is the product of the system transfer function and the input.
Oh, so for time domain it's adding. But
For time domain, it's convolution,
oh,
and it's multiplication in S domain.
Oh,
Okay? All right? Okay, so you have h of s here, and g of s in this specific question is given to be an integrator. So we just saw what is the impulse response of an integrator, and that's 1 over s. So you'll just substitute 1 over s over here. Okay? All right. Okay, now let's go over some other stuff. Now, another thing in terms of block diagram is when a difference equation is given to you and you need to represent that as a block diagram. Okay, so a similar question is in the 2009 exam. 2.1. Okay, so let me just do the same question. So y of n is equals to a of y n minus 1 plus x n minus 1. Okay, and remember that last time, or last time in the session, we had done an ideal delay system in z domain, right? So my input was x of n, my system was h of n, my output was y of n, and this is ideal delay. So this is also represented as z inverse, z raised to the power minus 1. Because my impulse response, that is h of n, is equals to 1 over z. This we had found in the previous problem solving session.
Is that because z minus 1 is the transform of the direct delta? Like, how, that's how it looks, how does the, I mean, the ideal delay.
So let's do this. Let's do this.
How does it look in this picture? Exactly.
So y of n will be nothing but x of n minus 1. I'll take the z transform of this. Okay, I'll get y of z, and I'll get z inverse x of z. So h of z is equals to y of z over x of z is equals to 1 over z, and it's our x of n is causal, so no initial conditions. That's why there's no initial condition here. All right, make sense? Okay. So coming back to the original equation, let me write that again. So we have y of n is equals to a of y n minus 1 plus x of n minus 1. All right, I need to represent this in a block diagram form. Okay, so at one end, let's just write, one second, y of n, right? This is our final result, right? Now, what are we getting? We have an input x of n, right? But here we have x of n minus 1. By how much do I have to delay it? 1. So I'll just write 1 z inverse, my ideal delay. This will cause a delay of 1. If I have 2 of these, I'll have a delay of 2. Okay? Or I can increase this power. Okay? And have that much amount of delay. Fine. Now this thing is added with this thing. And this is nothing but y of n delayed by 1. Right? So I'll take my y of n and delay it by 1. Also, it is multiplied with a. A is just a gain, it's a scalar. Alright, so now it's multiplied with a, right? And both of these are now added together. Okay?
So the shape of the box is the thing?
Sorry?
Shape of the box doesn't matter.
Yeah, so whenever you write gains, they are in these arrow-headed form. So if your input is, so this is your input, this is your output, again, input and output. Okay, so gain is always in these triangular box.
Gain as in like
A scalar multiplication.
Okay.
So gain is nothing but a scalar multiplication. Okay, A is scalar here. Right? And my delays are in these rectangular boxes. Okay? So let's just try another example. Any questions till now?
I got a question about the question before this one, which for GS we assumed we said that it was an integrator.
It's
right?
given in the question.
Yeah, but is it always 1 over s?
Yeah, so we had just done that. Here we had an integrator. My impulse response was u of t, so its transfer function will be 1 over s.
Okay, that's always the case.
Yes.
Fine.
Okay?
I'm
Yeah.
Okay, so the delayer that is in
Mm-hmm.
the discrete time domain, the delayer is d to the power minus 1. Then what is the C transform of that if it's already in terms of z? Like if you want to the z transform of that system, you know, x of n would become x of z, y of n will become y of z.
Yeah, so it will get multiplied with this, right? In z domain.
So yeah, so it stays the same.
Yes. So you'll have y of z is equals to a times z inverse y of z plus z inverse x of z. assuming no initial conditions. Okay.
But this one, well, because the differentiator, sorry, the integrator, it looked like the sigma. It looked like that, and then when you transform it, it became 1 over s. This one stays the same. It's z to the power minus 1 in both domains.
I didn't get it.
Like if you want to do the transform of that, if you want to transform that system to
So
zero,
here, if you're looking at this, this itself is a system. So in discrete domain, it's equivalent to a convolution, but in Z domain, it will become a multiplication.
Okay.
Okay? That's why it remains the same.
Okay.
Okay? All right. So don't get confused with the notations. Just remember convolution in time or continuous time or discrete domain becomes multiplication in S or Z domain. Let me get another example for you guys. And do go through the examples that are there on the review slides that was there for yesterday's lecture. Okay, I need to find it. Okay, so let's say we have y of n plus 2 plus 3y of n plus 1 plus 2y of n is equals to 6x of n plus 1 minus 2x of n. Okay? Now, this is in advanced form, so I'll just write it in a delay form.
Are you going to try to solve the equation?
Sorry?
Are you going to solve the equation?
No, I'm going to write the block diagram.
Okay.
Because you know the other thing of solving the equation already.
Does it have to be in delay form or?
Not necessarily, but that is the standard way it's generally drawn. Generally, it's like the ideal delay that you work with whenever you're drawing your block diagrams. So it's a good idea to delay it first and then write it. And mostly it will be given to you in a delayed form already. Okay. So we have y of n plus 3y of n minus 1 plus 2y of n minus 2 is equals to 6x of n minus 1 minus 2x of n minus 2. Okay. So my final output is y of n, right? So I'll just write y of n in terms of all of these. So I'll have 6x of n minus 1 minus 2x of n minus 2 minus 3y of n minus 1 minus 2y of n minus 2. Okay, so let me write a summation between, and I have x of n as an input, y of n as my output, right? So this is my output. Now there is no x of n term, so nothing goes in this direction. So first step is to delay. So I have an x of n minus 1 term, so I'll delay it by 1. So I'll have a z inverse, my ideal delay, and that will, multiplied with 6, and that will go in. Okay. Now, next is I'll have another delay term. Here I have 0 to minus 2 multiplied with the gain of minus 2, and that's added again. Okay. Now here I have y of n delayed, so I'll have, delayed by 1, multiply it with minus 3 and add it. Again, delay it by 2, multiply with minus 2 and add it. And that's your block diagram. Okay?
So can we delaying by 1, can we make it 2 branches
Yes, yes, you can do that also. So let me write that in that format. So I'll just write down the equation again. Ooh. So I have y of n is equals to, okay, someone dictate it. 6 of n minus 1.
Which one? 6n minus 1 minus 2x and minus 2 minus 3y and minus 1 minus 2y and minus 2
Thank you.
equal to y.
Yeah. So again, I have x of n. I can delay it first. So here my output will be x of n minus 1, right? So 1 will be multiplied with 6. Another branch will go out, get delayed again, and then get multiplied with minus 2. And all of this gets added. Okay? Similarly, you can do on the y side. Take y of n, delay it, and one term you'll have, which is this one, multiplied with minus 3. Again, take it again, delay it, multiply it with minus 2, and add it back. Okay?
So the previous one.
Okay? You can do it either ways. In the end, your result should be the same.
What did you change in this one? With the other one?
So here I have two separate delays. One is delaying by 1 unit, the other is delaying by 2 units. Here I'm just using the one that I've already delayed and delaying it again by 1 unit and going forward. Okay? All right. So that's how you'll approach with your block diagram questions. Okay?
Are they called different names?
What are called different names?
This one and the first one?
No, both of them are the same. Yeah. You can do either one of them. It's just which one makes more sense to you. Okay. So, just a few pointers on what all things you should remember. So, one is your circuit analysis, and refer to slide 17 in your lecture 23 slides. So just to summarize it, your R remains R, and whenever you go for circuit analysis, first of all, transform everything to the S domain. That's the whole point of studying it here. Okay? Don't start off in the time domain. So your resistor remains a resistor, your capacitor becomes 1 over CS impedance, L becomes SL, I believe. Right?
Yeah.
And your initial conditions, either do them as a voltage source or current source. So your voltage source will be in series with any of these components, and your current source will be in parallel. So this is for your initial conditions. Okay? And that's about it. And for op-amp, again, you can use the equivalent circuit given in the textbook. All right.
We can also just use ideal op-amp software directly, right? Without using the circuit. We are using the equivalent circuit.
Yeah. That's the equivalent circuit
Okay.
of your ideal op-amp. Okay? Now, don't forget some of your properties of Laplace and Z domain. So one is your differentiation property. And specifically it's time differentiation, because it's different property for frequency differentiation. So time differentiation, time integration. Alright, so just to give you quick examples of these, this is again in your midterm review slides. So let's say first that f of t is the time domain differentiation of e raised to minus at, sorry, sine omega t, right? So assume this to be f1t, and using your Laplace table, you know already the Laplace transform of this function, which is omega over s plus a, the whole square plus omega square, right? So now your f of s is just s multiplied with f1 of s minus your initial condition. And since we are dealing with causal signals, this goes to 0. Okay? So I'll have s omega over s plus a square plus omega square. That's your answer. That's it. Okay? And for the definition of causal system and causal signals is different. So when I say that a system is causal, that means the output of my system only depends on the present and past input values. But when I say the signal is causal, that means it's starting at 0. It does not have any initial conditions before 0. Okay? Another example of integration property is just a simple one. Ax cos omega x dx. So assume this is my f1 t. So my f1 t is now e raised to minus at cos omega t. My f1 s is, again, I'm using the tables directly, plus omega square, and my fs from my property is f1 s over s. Okay, so very simple implementation of our properties. Another thing, don't forget that your convolution becomes multiplication in S domain. Okay, and you have analogous Z domain properties. Okay, so for your Z domain, remember your left shift and right shift properties, and the convolution thing remains the same. Again, your convolution becomes multiplication in Z domain. All right?
I have a question on part A.
Yeah.
So I just want to clarify what we did. So
Sorry.
So from the table, we looked at e to the negative at sine omega t.
Correct.
And that's how we got omega over whatever that is. F1
Correct.
S. And then because we are differentiating, we do s f1s minus f1 of 0.
Correct.
Okay, so you don't differentiate it, then look at the table.
No.
Look at the table and then do the
Yeah.
Okay, cool.
Can you show the bottom real quick, please?
Oh, sure. Okay. Now let's just.
The left and right shift properties are only for the Z domain?
Yes. Okay. another thing that I had already discussed in the past was cascade and parallel realization of systems. So when I say cascade, it's so, let us say that we have two systems, H1s and H2 of S. Okay, these are two different systems. They have different impulse responses. So if I have an H of S given to me,
Cascade is series or parallel?
cascade is series and parallel is parallel. Okay, so if I have given H of S, let's say S plus 1 over S plus 5 and S plus 6. Okay, just an example. This might not be right. So there are two things that I can do. I can make a cascade realization or a parallel realization. Okay, and let me move on to the next page. So the H of S that I have is S plus 1 over S plus 5, S plus 6. So for cascade, I can do it again in two ways. So cascade is nothing but H1S multiplied with H2S. So let's say if this is my complete system, I'm writing this system as H1S followed by H2S now. And I can do that because convolution time domain will become multiplication here. Right? That's the idea I'm using. That's why I can do this. So here I can have H1S as S plus 1 over S plus 5 and H2 as 1 over S plus 6, or I can have H1 as 1 over S plus 5 and this is S plus 1 over S plus 6. Either of the ways. For cascade. Okay? Now for parallel, I will do a partial fraction expansion.
In parallel, I remember in normal time we added them, right? We added them.
Yes.
Is it the same when we transform them?
Yes. So in parallel, this is what I'm aiming for. So my input will be here, my output. Okay, so I have an addition in parallel. So my H of S is now multiplication of addition of H1 of S and H2 of S. That's why I do a partial fraction expansion to get this addition term. Okay, so my H of S will now be, let's say, sum A over S plus 5 and B over S plus 6, and we'll find this A and B, and this will be my H1 of S and this will be my H2 of S. Okay, or vice versa.
Okay, because then you're trying to reverse engineer it, because they tell you that you want this, and you have to say how you would go with cascade and parallel. So they give you a final result, and you have to find a way to build it. Right?
Yes. So the advantage of parallel is that it has less delay, because here my processing of H2S depends on H1S. Once this processing is done, then it will go to H2S and then you'll get an output. Here you'll get output from H1S and H2S at the same time, and then you just add them. Okay?
Yeah, and what was the problem with the other one?
So here you have to wait from an output from H1S for H2S to work. Right? Unless and until.
They work at the same time.
Here they work at the same time because the input is supplied at the same time. Okay? So this is a question that you already have in your exam. 2.4 part C, 2009. Okay? So let's do another block diagram example. So I have the following block diagram given to me. So you can either be asked to move from the block diagram to a transfer function and equation, difference equation, or differential equation, and from a difference equation to a block diagram. Okay, so either way.
Do we have block diagrams for continuous time? We don't, right?
No.
Block diagrams are only for discrete time.
For continuous time, we generally have it in S domain. Okay.
Are tap line delays okay with block diagrams or something different? Because it was on one of the older exams.
They're same as the block diagrams.
Okay, it's just like another name or something.
So a tap delay line is just like if I take my input and delay it a lot of times, right, in succession, one after the other, and then add all of it together. That's my tap delay line. Yeah.
The continuous time doesn't have block diagram?
So in differential form. So if I give you a differential equation, how will you write it as a block diagram? Yeah, so that's not a question that you can expect. Mostly you have a difference equation that will be given to you, and that you have to draw as a block diagram. Or for continuous time, you can have a block diagram in S domain, and you'll be asked to get a transfer function. All right, so here we have to find the transfer function. What will be my first step?
You can say y of s is equal to vs times k.
Okay, so let's say first equation I have y of s is k times v of s. Next,
Vs is equal to rs times 1 over s.
v of s is equals to r of s over s. Next,
R of s is equal to x of s plus y of s.
r of s is equals to x of s minus y of s.
Yeah, that's
Be careful with these
Yeah,
signs.
the two things are little and they change everything.
Yeah, so this plus corresponds to this and this minus corresponds to this. Okay, so be careful with these signs that you have. Okay, so now what do I do?
We put them in a calculator.
No, that's something that you don't want to do. Okay. Yeah, so we'll do substitution one after the other. So first I'll substitute r of s. Okay, so I'll have s v of s is equals to x of s minus y of s. Okay, so sorry. So let me number these equations. So substituting 2 and 3, I get this. Okay, now I'll substitute 1 in this equation, 4. Okay, so now what do we have? My v of s is equals to y of s over k. So s y of s over k is equals to x of s minus y of s. Get y of s on the same side. So I'll have 1 plus s over k. Y of s is equals to x of s. My transfer function h of s is y of s over x of s, which is k over s plus k. That's your answer. The end. Okay? All right. Let me see. That's it, I guess. That's it, I guess. Okay? Let me know. I'll be here for more questions.
Can we expect questions like purely from someone like a discrete time convolution question or something like that? Or does it have to be a question that has some like limitation, but it's material?
get a time frame?
You just don't get out of touch of your midterm one. If he runs out of questions, he might just put midterm one.
Yeah.
Oh yeah, I was gonna do that today and I woke up.
I don't think so.
Didn't she just say that?
She just said like that she's not. Make sure you're related to different stuff.
So it's possible.
Yeah.
That's the interpretation.
I hope not.
I hope not too. Do you remember what she said about the causal system and how they signal?
It's like the output starts at 0 from different angles. It's like current or past values. Unlike the regular.
You need to know directly before and directly after. Yeah, I got it.
I think I like different answers, see, but different
system
Depends on the input, like past and present signals. Want to go continuously?
This one is better like this. Your energy really makes a lot of difference.
Sleep what we told. I'm only gonna sleep like 4 hours tonight. Oh, you have number theory too, right?
That I know, but I don't know.
That's always the case.
Supposed to be like the one. Oh, okay. Okay, I just wanted to make sure. Alright, I just wanted to know that.
Yeah. I went to Dr. Jones.
That makes sense. We know A equals 0, B equals 1, and C equals 0.5J, and C star equals 0.5J. However, negative points are you can write it, you get 0.5. Yeah, I'm leaving now. I'm just hacking.
Water weight
You're eating right now, are you drinking it?
Wait, so this is actually this would be considered like 0 minus 0.5J, right? Like the C right here is negative 0.5J. Is that in polar form or is that in rectangular? Oh, what are those? Okay, so that's not actually written in rectangular form then.
That's not rectangular.
Oh. Okay. I don't know. Okay.
So the discussion with holes. So the holes basically that's up to us. So here it was given to us like this, so we don't bother simplifying. So we just put both at 1, and if we do simplify it, it's simply just that. Okay. Let's see. And we're running. Oh, you mind if I just take a look at the average?
Bye bye, thanks.
All the best for exam.
here they just set S equal to the frequency, like.
Yeah.
But for like impulse response or like step response, that just means you knew what the input signal was, which is like x of t is u of t, or it's x of t is the direct delta function. So like I don't understand how you could just plug in S
So
to be that.
the type of signals we are dealing with, the calls of signals, that allows us to make the substitution.
Okay, so if this asks for like the other formula for the step response.
So for step response, that's a different thing altogether.
Oh.
For that you use x of t as a step function and then get your step response.
Oh. Okay. So this frequency response is by itself because it's not.
What you get from your Fourier transform, that's your frequency response. But that one you guys will not study. So you can go from S domain to frequency domain, Z domain to frequency domain, making these substitutions.
Just by plugging in S equal to pi of j. Okay.
And several questions. You have a question?
Yeah, I just wanted to show. So I was trying to solve for the C, and in solving for the C, first what I did, so I got the A, B, C, C star, and then I solved for the A and B. I did it on a different page, but I just kind of came over. But I equals 0, B equals 1, and I don't know how I got it in this format, but I think my calculator gave it to me in this format. But if it's like this, like 1 over x squared minus 1 over this, then I just split it up to where like I just use this for this part and then use this part for this part, because they're equivalent, right? So I should just be able to split it up like that, because addition. So I did that,